Okay, so last time we talked about the adjoint action. So let's go over some of the key points. So G is a linear algebraic group. We had the Lie algebra of G, which is the tangent space at the identity. So derivations from the affine algebra to the one-dimensional module, which is just the fiber at the identity. And we saw that the bracket comes from this, the dual of the affine algebra of the group. So we define the adjoint action as follows. So we take the conjugation map by little g, we differentiate that, and since the conjugation map takes the identity to the identity, we get an endomorphism of the tangent space of the identity, and that's the adjoint action. That endomorphism defined by little g is the adjoint action of little g on the Lie algebra. So that's when we think about the Lie algebra as the tangent space at the identity. The adjoint action has these different realizations if we think about the Lie algebra as left invariant or right invariant vector fields. So for left invariant vector fields, we conjugate by rho sub little g. Rho sub little g being this algebra automorphism of the affine algebra of G, defined by the right multiplication action. And we also had lambda G, which is coming from the left multiplication action of G on itself. And if we conjugate a right invariant vector field by lambda G, that's its adjoint action. That's the adjoint action of little g. So we proved that these three actions are all actions by Lie algebra automorphisms, and that they're all identified when we take the isomorphisms when we trace through the isomorphisms between these various Lie algebras. So that's the content of this proposition here. We have these isomorphisms. So we had that. We went through the proof. And then, we had some examples. So this adjoint action turns out to be just conjugation in many cases. So for GLN, it's on the nose, it's conjugation by an invertible matrix, because the Lie algebra can be identified with all matrices. For SLN, we have that the Lie algebra is traceless matrices, and again, the adjoint action is given by conjugation. And we also saw the example of the orthogonal group. So we had that there. So here we had the little subtlety that we need to make sure that we're conjugating by an orthogonal transformation, not just any matrix, for the condition for the Lie algebra to be preserved. And the adjoint action is trivial if and only if the group is commutative. So then we had this proposition that says that, so we saw that we had all, okay, so first of all, TG is all the vector fields on the group. So all derivations from affine algebra to itself. And so this is something quite big. We were considering inside of this space of vector fields, the left invariant ones and the right invariant ones. Those are each finite dimensional, and we saw that those can be identified with the tangent space at the identity, and they have a Lie subalgebra structure. And in fact, this proposition is telling us that any vector field on the group can be built out of a left invariant or right invariant vector field if we just allow ourselves to vary the functions, if we allow ourselves functions on the group G. So more formally, if we just take the tensor product of the affine algebra, so all functions on G with left invariant vector fields, that gives us all vector fields. So I gave you one idea of how to look at this. You can also take a look at Springer. His approach is a bit different, but pretty much equivalent. Right, so we had that. And and the connection with the adjoint action is that if we look at a left invariant vector field, and then we kind of want to think about it as a right invariant vector field, but we need to make some correction, and this correction is given by the adjoint action. So this correction at a single point on the group is given by the adjoint action. So that's this diagram commutes. That's what it means. So if we take let's see here what xi is. Yeah, xi is just an element tangent space with identity. We can apply alpha L to think of it as a left invariant vector field. And then we can think about what happens at a point little g. And then we can compare that to the corresponding right invariant vector field. But in order to get the right thing, we need to apply, oops. Sorry, just give me a second. Oh, I'm still sharing the screen, right?
Yes.
Okay, thanks. So in order to get the right thing, we need to apply the adjoint action of little g to xi, and then we get the right thing at that point little g. If we move the point little g, then we will have to apply a new transformation to xi, and that transformation is the corresponding adjoint action over that point. So that's the idea here. And then I collected all these facts. So yeah, so the dimension of the Lie algebra is equal to the dimension of G. If we have a closed subgroup of G, then its Lie algebra is a Lie subalgebra of the tangent space with identity. And if we have a morphism between linear algebraic groups, then we get a Lie algebra homomorphism between their Lie algebra. So, and this is just differentiation at identity. So that's all fine. And then we had this fact that if we have a so this is just a special case of the previous thing. So if we have a representation of the group, then we get a representation of the Lie algebra. And I mentioned this equivalence of categories. Don't worry about it too much. I guess the important thing to understand is just that if you have a representation of G, then you can produce a representation of the Lie algebra. And then there's some machinery behind the scope of this, beyond the scope of this class, that lets us characterize the representations of the Lie algebra that come from the group. But yeah, don't worry about it too much. And then we also had the fact that the Lie algebra of a product of groups is the direct sum of the Lie algebras, and the differentiation of the multiplication map is addition of the addition on the Lie algebra of vectors in the Lie algebra, and the inverse map, when we differentiate it, we get just negation. So xi goes to minus xi. Okay, and then I talked about the universal enveloping algebra. Again, this is, I guess, I don't think I'll ask you any homework questions or anything about universal enveloping algebras. So if this part is too unfamiliar to you, then yeah, don't worry about understanding all the details, but it's just for exposure. So if you continue with studying representation theory, then you'll come across universal enveloping algebras, and it'll be good that you have at least seen them once, even if you don't work with them too much right now. Okay, so the idea was we take the tensor algebra of so anytime we have a vector space, we can take its tensor algebra. So this is kind of like this free algebra with multiplication given by concatenation. And we can produce various algebras by taking quotients of the tensor algebra. So there's the symmetric algebra and the exterior algebra. So these satisfy some universal properties. So yeah, I won't go into the sort of categorical language that describes the properties of these algebras, but they're somewhat canonical, and they come up a lot. So the symmetric algebra is a commutative algebra where we take the tensor algebra and we quotient out by this relation. The exterior algebra is skew commutative. So V tensor W is equal to minus W tensor V. And we get it by quotienting out the tensor algebra by this ideal. And to get the universal enveloping algebra, we start with not just any vector space, we start with a Lie algebra. And then we take the quotient by this ideal generated by all xi and xi prime in the Lie algebra. And this says that the commutator, so sort of inside the tensor algebra, we have this sort of notion of commutator. Take two elements, multiply them, and then subtract their product in the opposite order. And in the Lie algebra, we have this sort of commutator. So note that the commutator in the tensor algebra is a 2 tensor, and the Lie algebra commutator is just another element in the Lie algebra. So it's something in G. And we set these two things equal to each other in the universal enveloping algebra. And we saw that there was some nice properties. So if G is commutative, then we recover the symmetric algebra, because on this right-hand side, we just get 0 for all xi and xi prime. Unlike the tensor algebra, the symmetric algebra, and the exterior algebra, the universal enveloping algebra is not graded, but it is filtered. And so these are the relations for the universal enveloping algebra of SL2. And if you're curious and you want to get comfortable, you can try proving that this element is central in the universal enveloping algebra of SL2. In fact, it'll generate the center. The center will be just polynomials in this element, which is known as the Casimir operator. Okay, so maybe there was this adjunction, but maybe I won't talk about this in any more detail. So any questions about the material from last time? Okay, so again, universal enveloping algebra stuff is just kind of extra things to maybe make you curious, but if it's too unfamiliar to you, then you can skip it. So now I'll move to the next set of notes. Okay, so far we've seen, so in the last few lectures, we saw how we can start with a linear algebraic group, and we can define the Lie algebra of the linear algebraic group. And I guess we won't talk too much about some of the specific results that we get from this association. I'll probably mention them a bit later. But the next thing we'll do is we'll talk about how to start with a linear algebraic group and consider various quotients of the group. And it's especially interesting when the quotients are somewhat small in a certain sense. So we'll see that in today's lecture, we'll see the notion of a complete algebraic variety. And a complete algebraic variety is similar to a compact Hausdorff topological space. So if we have so compact topological spaces are often easier to understand because we can use various tools there that we can't use for an abstract topological space. And in a similar way, complete varieties have some better behavior that we can exploit, and we can understand a lot about the group by looking at these quotients of the group that are complete varieties. So quotient by a subgroup. I mean, so if we take a linear algebraic group and we take some closed subgroup and the quotient is complete, so you can think of it as compact, something kind of small, then that subgroup is called a parabolic subgroup. So we'll introduce parabolic subgroups today, and I guess that's what I wanted to say about motivation. And we can jump right into the notes. So if we have a linear algebraic group and a closed subgroup, then there's a notion of a quotient of G by H. So so the definition will be quite formal. We'll be a bit more concrete in a bit. So the quotient is a pair X, so capital X and lowercase x, consisting of a homogeneous space for G. So X is a homogeneous space for G, and the point little x in the homogeneous space, such that the following universal property holds. So anytime we have another homogeneous space and a point in it with H, so H hasn't appeared so far, here's where H appears. H is a subgroup of the stabilizer of little y and G. Then there exists a unique map from X to Y such that f of X is equal to Y. So G equivariant map. So yeah, so that's the definition. You can also say that this pair is initial in the category of pointed homogeneous spaces that have H in the stabilizer of the point. So pointed homogeneous spaces is just a pair X G with X being homogeneous and little x being in X. Yeah, so this is kind of an abstract definition. The point, we could have just said that that the quotient is just a coset space, but the problem is that we don't, to begin with, a priori we don't know that this is an algebraic variety. This is just some set. And in algebraic geometry, we want to do things always in the category of algebraic varieties. And if we forget about kind of the coset space and we think about what's the universal property that the quotient should satisfy, then that's how we get this definition. Okay, so this is some abstract nonsense. The upshot is that quotients always exist. So if we always have a closed subgroup, then we can always perform the quotient operation, and we get a algebraic variety. So I won't go into too much detail for the proof of this theorem, but let me give you the idea of the construction. So if we have a closed subgroup, then functions on the subgroup is a quotient of functions on the group. So we have some ideal I, and so let's let V be a finite dimensional subspace of the affine algebra of the group that contains a set of generators for the affine algebra as an algebra. So this is similar, if you remember the proof of the embedding theorem, that any affine algebraic group embeds inside of GLN. This is, we started with a similar consideration here. So we take such a finite dimensional subspace, it contains generators, and we also require that it's stable for all the row G's. We can, yeah, and we argued previously that there is such a finite dimensional subspace. Okay, anyway, so we take this V, we take W intersect I, so remember I is the defining ideal of H, and you can argue that H is exactly those G's. H consists of exactly those elements of capital G, such that rho sub X of W is equal to W. So yeah, so I won't go into details there. I think I think it sounds believable. There's some things to check, but yeah, so that's what one needs to show. And okay, so now we kind of understand H in terms of this subspace W. So now let's take this subspace W and let's take its exterior power, and let's also take so let D be the dimension of W, then the dth exterior power of W will be one dimensional. So this is a general fact. Anytime you have a vector space, you can take its various exterior powers, and if you take the exterior power that's the dimension of the vector space, then you just get something one dimensional. So more concretely, if you take a basis for W, W1 through WD, then the tensor W1, tensor W2, tensor all the way up to WD, that generates that generates the dth exterior power. And yeah, okay, so we get something one-dimensional. I invite you to think about it more if you're not convinced. We take the dth exterior power of V, which is something in general more than one-dimensional, but since D is less than the dimension of V, it'll be a non-zero vector space. And so now what happens is so V was, we chose V to be invariant under all of these row operations, row Gs. And so V itself is a representation of G via the rows. And so what we can do is we can take the dth exterior power of the rows, and that gives us a representation of G on this exterior power. So yeah, so this is the explicit formula. We just act by row G on each component of a simple tensor. So yeah, if you're not familiar with this notation, I'm taking this denotes the image of V1 through Vd in the tensor algebra, the image of that inside the exterior power. Okay, so then one argues that if we take this one-dimensional space, which I'm calling L, that X will be exactly those elements in the group G that take L to itself under this action. Right, and so now we do this trick where we take the projective space of the dth exterior power of V. So the projective space, you'll recall, is the projective space of a vector space is all the one-dimensional subspaces of that vector space. So we take all the one-dimensional subspaces of this exterior power, and the line L that we had is a specific one-dimensional subspace. So it defines a point in this projective space. So I'm calling that point little x. Maybe it's a bad notation because I was also using little x for things in the group, but anyway, too late to change it now. So we have this point in the projective space, and one argues that the stabilizer of that point under the natural G action is H. So G acts on this G. So the dth exterior power of V is the representation of G. So G acts linearly on that vector space. So in particular, it takes lines to lines. So that gives us an action on the projective space. And you argue, this is basically reformulation of this conclusion here, that the stabilizer inside of G of this point little x is exactly the subgroup H. All right, so then, so why is this what we want? Then what we do is we take the orbit of little x inside of this projective space, and since the stabilizer of this point is H, this orbit will be G mod H. So it'll be a homogeneous space with where the stabilizer of a point is H, and you can go through and check that it satisfies that universal property. So yeah, so that's the construction. So this is a way to realize this set of cosets G mod H as an algebraic variety. And in fact, we see from the construction that it's a quasi-projective variety. So it's the intersection of an open and closed inside of a projective variety. And its dimension is the dimension of G, and the difference of the dimension of G and H. Yeah, and also if H happens to be normal so this is a fact, maybe a proposition that I'm not really going to prove, but it's a fact that if H is normal in G, then this quotient space is in fact affine. And it has a natural structure of a linear algebraic group. So yeah, I mean, normal subgroup in G means the quotient is a group. And why is it a linear algebraic group? Well, it's you basically show that there's an embedding of G mod H inside of GLW. So W is this space from before.
Can you just
Sure.
remind us why L is one-dimensional?
Right.
Didn't see
So
explanation.
yeah, so L is one-dimensional because it's a general fact that if you take vector space of dimension d, then its dth exterior power is one-dimensional.
Oh, determinant. Okay, now I see.
Yeah, it's exactly the
Determinant.
determinant. Yeah, that's exactly right. Okay, any other questions? All right, so yeah, so the upshot is that the quotient is, we have a quotient as a variety, it's quasi-projective. If H is normal, then it's another linear algebraic group. Okay, so now I want to move on to complete varieties. So this is section 6.1 in Springer. So I said already a few things about complete varieties. So now let me say them more formally. So an algebraic variety X is complete if for any algebraic variety Y, this projection map from X cross Y to Y, so just projection onto the second coordinate, is a closed morphism. So it takes closed subsets of the product to closed subsets in Y. So that's what complete means. So it seems a bit strange, but it turns out that, as I remark here, completeness in the category of algebraic varieties is analogous to compactness in the category of locally compact topological spaces. So there's an exercise, one of the exercises in section 6.1 that explains why this projection condition here, being closed morphism in the category of locally compact topological spaces, is equivalent to being compact in that category. And yeah, so that's some topological motivation, but here we want to think about algebraic varieties, and we can't do the same tricks that we usually do with locally compact topological spaces, so we need this definition. All right, so so that's the definition. First example, so the claim is that, is there a question?
Yeah, I have a question about the previous proof.
Oh, yeah.
You said it was a quasi-projective variety, and I see why it's open, but why would it be closed if we have to have a special property about the image being closed after this?
So it's an orbit of the group G, and so any orbit is intersection of an open and closed inside the variety, and so it's a projective variety. So any closed subset is projective, and quasi-projective means open inside of a projective variety. Does that answer your question, or was your question something different?
Well, I guess I want to know why explicitly it's Zariski closed.
It's not Zariski closed inside the projective space. It's not, yeah. If it were closed, then it would be a projective variety. There is a closed orbit though. So, I mean, if we do this, anytime we have a action, well, no, that's, yeah, anytime we have an action of a group, there is a closed orbit. But yeah, it's not Zariski closed in general.
Okay.
Yeah, we'll see some examples later on. Maybe it'll become clear. So, okay, so let's Any other questions about?
Yes, can I ask
sure.
about the
Yeah.
definition of compact in as a variety? Because I know that quasi-compact is what you use for open covers. So
So we're not too concerned with the definition of compact, except for this sort of intuition from topology, but in algebraic varieties, that definition doesn't really work, and we need this definition. I don't know if yeah, go ahead.
Just because I know that the AN is supposed to be not complete for greater n, but if you look at the definition of compactness, that for every open cover there is a finite cover, then it is quasi-compact. So I was wondering, when you're talking about compactness here, what definition do you mean?
Oh, okay. I think I understand. So I only mean when I said compactness, it was only in this other category of locally compact topological spaces. So in that category, we have the definition you were saying, that every cover has a finite subcover. But the point is that definition doesn't transfer nicely to the realm of algebraic varieties, and we need a different definition there. And yeah, so we forget about this. So we forget about this notion of compactness from topology that we're more familiar with, and we focus on this completeness. So I'm not going to use, the only reason I said compact is because this is kind of an analog, but I'm not going to use compact anymore in the setting of algebraic varieties.
Okay, thank you.
Yeah, I'm not sure if that really answered your question, but I hope it helps a little bit. Okay, any other questions? Okay, so we have this. So,
I have a question.
so we have an example of a variety that's not complete. So A1 is not complete. In fact, yeah, as Shai just mentioned, AN is not complete for any n. So why is A1 not complete? Well, so what do we need to show? We need to exhibit a variety Y such that the projection from A1 cross Y to Y is not a closed morphism. So what's the Y that we choose? We choose another copy of A1, and we have this projection map. And what's the closed subset that we choose? We choose this closed subset. So this is isomorphic to the multiplicative group, but we don't care about the group structure right now. So just all the pairs of elements whose product is 1. And if we look at the projection onto the second coordinate, then that's everything except for 0. And the complement of 0 inside of A1 is not Zariski closed. So this map is not a closed morphism, and so A1 is not complete. And if this same sort of argument, you can just extend it with more coordinates, you can show that AN is not complete. And it's a fact. So this is an example of a variety that's not complete. What about something that is complete? Well, any projective variety is complete. In fact, it's enough to show that Pn is complete. And you can, so I won't go through the proof, but you can look at 6.1.3, they prove it there. So Pn is complete. So again, okay, and this is analogous to the fact that from topology, from basic course in algebraic topology that you saw, that Pn is compact as a manifold. So that's why this is, I guess, kind of believable. Okay, so we need a few.
Can I have a question?
Sure, yeah.
if the variety is compact, is it always complete?
If what variety is compact?
If a variety is, for example, an algebraic variety is compact, is it always complete?
So I guess this is sort of I always get confused by this. So compact, I mean, there's this pedantic thing where you don't want to. The word compact is reserved for locally compact topological spaces, and the and algebraic variety is not locally compact in general. So yeah, I'm not sure. I don't. Yeah, maybe I'll duck from your question because I don't want to get. I'm not sure, and I get confused by the definitions. Let me just say it's subtle.
Okay.
Yeah, you can look back to some of the discussion in chapter 1 about this sort of stuff. Okay, so okay, I think as a general thing for working with algebraic varieties, I think it's generally useful. I don't want to say always, but I would think generally useful to just forget about the notion of compactness from usual topology and just focus on completeness and on the analogs of those notions in the context of algebraic varieties. Okay, so let's collect some facts about complete varieties. So if we have a complete variety, X is a complete variety, then any closed subvariety of X is also complete. That's the first part. Second part is if we have a morphism from a complete variety to another variety Y, no assumptions on Y other than that it's an algebraic variety, then the image is complete and it's closed inside of Y. And finally, if X happens to be affine, in addition to being a complete variety, then X is finite. So the only complete varieties that are affine are finite varieties. Okay, so for claim 1, it just follows from the definitions because the definition is some statement about closed sets, and if we think about a closed subset of X, we get the right thing. So what about number 2? Well, to prove it, we kind of factor F into two maps, into an inclusion and a projection. So the map F is first the inclusion of X as the graph inside of X cross Y. So X goes to X comma F of X inside of X cross Y. That's the graph. And then we project onto the second coordinate. And so that composition is just F. Okay, so now the image of this map is the graph, and it's closed inside of X cross Y. So the reason it's closed goes back to our discussion of algebraic varieties. The graph of any morphism between algebraic varieties is closed. That comes from this separation axiom that we had. So it's closed and it's isomorphic to X itself. So the graph is complete. And now the image, so the image of F of X lies inside Y, and it's the same as the image of the graph under this projection map. And so it's closed because X is complete. So anytime we take a closed subset in X cross Y and project onto Y, we get something closed. In particular, we take the graph, which is closed, and project. The image is F of X, and that's closed. So to see that it's complete, so it actually takes a little bit of thought. So let's take any variety Z, and we take a closed subset in X cross Z. Then the sorry, let me make sure this is right? Just a second. I think yeah, something not quite right here. Yeah, I think what we want is to take actually we want to take V to be closed inside of f of x cross z, and then yeah, and here we also should have f of x cross z, not x, and then it works. I think then the image. Yeah, so in these two instances, we have to replace x by f of x, and then I think it's correct. So we use the fact that the pullback of any closed set under an algebraic, under a morphism of algebraic varieties is again a closed set. Okay, so yeah, I'll clarify this. Maybe I'll send an email. So we get that the image is complete. So right, and then for the third part, we need to show. So the third part claims that any variety that's both affine and complete is just a finite set of points. So let's consider the case. So let's assume x is complete and affine. It's enough to consider the case when x is also connected. So then let's take a function on x, so an element in the affine algebra. So then it defines a map from x to a1, so just a function on x. And now the image has to be complete and closed inside of a1. That's what we proved in 2, modulo the modifications that I need to make. So it's closed and complete inside of a1. We already know that a1 is not complete, so the image must be proper, and it's also connected. And so the only things that are proper, connected, and closed inside of a1 are just points. So that means that f is constant. F maps everything to a point. The image of f is a single point. And f was just arbitrary inside of the affine algebra. So that means that everything in the affine algebra is just a constant. And so the affine algebra is just k. And so x is a point. Right. So that proves the third part. And right. So you may be wondering. So okay, so also I have this theorem, which again I won't prove, which is that if we have a connected algebraic group that's complete as a variety, so this is a course on algebraic groups, so you may be wondering what are the algebraic groups that are complete, so in that case the theorem asserts that this variety must be commutative. And the groups that arise in this way are called abelian varieties. And they're kind of orthogonal to linear algebraic groups. So linear algebraic groups are affine as varieties, and abelian varieties are complete as varieties. And we just saw that the only things that are both affine and complete and connected, I guess, is a trivial group. So the only group that's both a linear algebraic group and an abelian variety is the trivial group and connected, I guess. So yeah, so this course is about linear algebraic groups, but so abelian, we won't say anything more about abelian varieties, but it's good to be aware of this notion. Okay, so that's kind of the facts we need about complete varieties. Yeah, any further questions before we move on? Okay, I know it's kind of maybe a lot of new material, but yeah, let's move on. Okay, so next section is about parabolic subgroups and Borel subgroups. So in this case, so in this section, we're going to have G be a fixed linear algebraic group. So definition, a closed subgroup of G is called a parabolic subgroup if the quotient is complete. So P is a parabolic subgroup if G mod P is complete as an algebraic variety. So one thing to note is that an equivalent, this definition is equivalent to asking that G mod P is projective, projective variety. And that's because we already know that all these quotients, like closed subgroups, are quasi-projective. And if we have something that's complete and quasi-projective, that's equivalent to asking that it's projective. And yeah, so anything that's projective is complete. And so then, yeah, so subgroup P is parabolic if and only if the quotient G mod P is projective. If you like that definition better, then you can stick with that definition. All right, so what are some examples? So in GO2, we can look at the upper triangular 2x2 matrices that are invertible, and the quotient, so that's a closed subgroup as we've already seen, and the quotient is just P1. So why is the quotient just P1? Well, we have the action of GO2 on K2 on the two-dimensional vector space, just by matrices acting on two-dimensional vectors. And this is a linear action, it's a representation. And so in particular, it takes lines to lines. So any line in K2 gets sent to another line under the action of any element in the group. And that means we get an action of GO2 on P1, P1 being just the projective space of K2. And you can also see that this action will be transitive. So if we have any line, there's some element of the group that takes your standard line, let's say the span of the first basis vector, to that line. So any two lines are related by an action of the group. And if you compute what the stabilizer of the line spanned by 1, 0 is, then it's just B. So that's pretty easy to see. So this is a fairly simple argument, and we'll see variations of this argument soon enough. So that proves that this subgroup of upper triangular matrices is in fact a parabolic subgroup. Okay, and similarly, if we think about the upper triangular, the subgroup of SL2 consisting of upper triangular matrices, so of this form, then in fact the same argument as before shows that the quotient is P1. So it's the action of up here we noted that the action of GO2 is transitive, but in fact already the action of SL2 is transitive on P1, and the stabilizer of this point of this line is B1. So yeah, so that's a parabolic subgroup, and I think, yeah, maybe this is a good time for a break. So let's take a 5-minute break, and then I'll continue with more examples, and I'll ask if there are any questions. Okay, so any questions on the definition of parabolic subgroup or these first two examples? All right, let's move on to the next example then. So we have GO3, and so I want you to consider these following subgroups. So P1, so these are all the matrices of this form, so zeros in the first two entries on the bottom row, and anything you want elsewhere as long as the determinant is non-zero. P2, we have zeros in the last two entries of the first column, and anything else in the other entries as long as the determinant is non-zero. And B is upper triangular invertible matrices. So the product of the diagonal entries has to be non-zero. So, okay, so the claim is that each of these three subgroups is in fact a parabolic, So how do we see this? So first of all, if we take the quotient of G by P1, then we get the Grassmannian of two planes in K3. And the way to see this is similar to before. We have an action of G on K3, a representation. This representation takes two planes to two planes, so we get an action of G on this Grassmannian, and the stabilizer of a point of your sort of a two plane, so of the somewhat canonical two plane, the span of the first two basis vectors, that stabilizer is going to be P1. And in fact, the Grassmannian is isomorphic to P2, this Grassmannian. Anytime you have one less than the number of dimensions, so the Grassmannian of hyperplanes in a vector space is the same as lines in that vector space as an algebraic variety, so that's P2. So it's in particular projective. And with this second subgroup here, we do a similar sort of thing, but we just look at lines inside of K3, and we get that this is the stabilizer of the line span by the first basis vector is this subgroup P2 here, and the quotient is projective. And for this last subgroup of upper triangular matrices, then the quotient can be identified with the following. So it's the set of all pairs, V1 and V2, where V1 is a line in K3 and V2 is a two-plane in K3. So something in the Grassmannian 1,3 and something in the Grassmannian 2,3. But not just any pair. We have the condition that the line is contained in the plane. So this is a line and a plane inside of K3 such that the line is contained in the plane. So to see why this is okay, so here, yeah. So again, G will act transitively on. So first of all, G acts on this product, and if we look at the subspace of that product where this condition holds, V1 is contained in V2. That condition is preserved by the G action. So anytime we translate if we have a line and a plane containing that line, when we act by G, we'll again have that pair will be taken to another line and another plane with the line contained in the plane. And in fact, the action is transitive. And the stabilizer of, so as I said before, the stabilizer of the two plane spanned by the first two basis vectors is P1. The span of the first basis vector has stabilizer P2. And then if we look at the span of the first basis vector as a line that's contained in the span of the first two basis vectors as a plane, that the stabilizer of that inside of the group will be exactly upper triangular matrices. So B. Okay, so yeah, so that's that's this example. Feel free to work it out a bit more to convince yourself that the action is transitive here. Now there's one more thing we need to show, and that this variety is closed inside of P2 cross GR23. So and yeah, that's, I won't go through the details here. There's actually an exercise that I'll assign that kind of does some of the work for this, but it's closed. This is a closed condition. In fact, you can think about it yeah, there's various ways to think about it. Maybe I won't go into too much detail now, but that's a closed subvariety of P2 cross P2, and hence it's a projective variety. So P2 cross P2 is a projective variety. And a closed subvariety of a projective variety is again a projective variety. Okay, so we see that these three subgroups are all parabolic subgroups of GL3. And this example of GL3, any questions on this example? Does it make sense? At least the general feel for the argument? Okay. So in general, for GLN, we have the flag variety. So the flag variety is the following. So it's a subvariety of the product of the Grassmannians. So we have the Grassmannian 1n up to the Grassmannian n minus 1n. So it's a subvariety, and it's a subvariety of all points in this product of Grassmannian that satisfies certain properties. So first of all, what's the point in this product of Grassmannians? Well, it's a line, so one plane, a two plane, a three plane, all the way up to n minus one plane, so a hyperplane. And to define the flag variety, we need the condition that VI is contained in VI plus 1. So we have a line contained in a plane. The plane is contained in a three plane. The three plane is contained in a four plane, and so on. And we keep track of all this information, and that's the flag variety. This page turned out to be a bit blurry. Sorry about that. I think it's still readable though. So one can check that each of these Grassmannians is a projective variety, and the flag variety is in fact closed in this product of projective varieties. So this is a closed condition here, and therefore the Grassmannian therefore this flag variety is a projective variety. So that's some algebraic geometry. I think there's an exercise in the book that I'll assign that goes through that with some hints, and so that's the first part. The second part is that there's an isomorphism between the flag variety and G mod B, where I don't know if I said B is upper triangular matrices. Oh yeah, here it is. B is the subgroup of upper triangular matrices. So again, to show this, you just show that there's a transitive action of G on the flag variety, and the stabilizer of a certain point is B. What point do you take? Well, you're going to take the point that has the first basis vector as the one plane, the span of the first basis vector as the line, span of the first two basis vectors as the two plane, span of the first three basis vectors as the three plane, and so on. So yeah, so so this is what I already said, and this point on the flag variety is called the standard flag. There was a reason, I just remember, I meant to look this up. There was a reason why this is called the flag variety. I think I'll look it up. I remember reading in a book once why this name flag variety stuck. So that stabilizers B, so the flag variety is G mod B. And this subgroup of upper triangular matrices is a parabolic subgroup of GLN. Okay, so hopefully through these examples, you got a bit of a feel for some parabolic subgroups. Any questions on this last example? I know it's kind of involved. Okay, so we need a few facts about parabolic subgroups. So first of all, G itself is a parabolic subgroup of itself. And second fact is, if G is commutative and connected, I guess, then its only parabolic subgroup is itself. And third, if you have a parabolic subgroup and you take any conjugate, then you again get a parabolic subgroup. So these, actually this proposition is not too difficult. So first, for the first part, it's pretty easy because G mod G is a point and a point is complete. So there we go. For the second part, if we take G to be commutative, then any closed subgroup of G is normal. So any subgroup of a commutative group is normal. So the quotient must be an affine variety. So I indicated earlier today why the quotient by a normal subgroup is affine. And so this quotient is complete if and only if this quotient is both affine and complete, and that only happens if it's a point. So then G is, the parabolic is all G. And for the third part, you can just write an explicit isomorphism between G mod P and G mod any conjugate of P. So
Can you say?
Yeah.
Can you just say to which kind? What is the analog for parabolic groups? For example, center-free groups. I don't know what is a good analog.
Analog in which
To
context?
parabolic, to the parabolic variety, to when a group have a parabolic subgroup.
What sort of group? What I mean, in compact Lie groups, then it's a subgroup of a compact Lie group. No, maybe. Yeah, maybe I can answer your question in a little bit once we have a bit more machinery.
Okay.
Yeah. Okay. Remind me if at the end of the lecture, if I haven't said anything about it, remind me.
Okay. Thank you.
So, okay. So maybe I can just say, so for compact Lie groups, I'll say later on, but for yeah, for if you think of non-compact Lie groups, so like GLN over complex numbers or over the real numbers with the usual topology as opposed to the Zariski topology, then the analog is that the quotient must be compact as a manifold. So that's the analog for those sorts of groups. For compact Lie groups, I'll say a bit later on.
Okay, thank you.
So okay, so we need a few more facts. So let's suppose we have closed subgroups P and Q in G, where P is contained in Q. First assertion: if P happens to be parabolic in G, then Q is automatically parabolic in G. Second assertion: if P happens to be parabolic in Q as a closed subgroup of Q, and Q happens to be parabolic as a closed subgroup of G, then P itself is parabolic in G. So it's some sort of transitivity. So for the first assertion, you just use the quotient map. G mod P goes to G mod Q. This is a surjective map. If G mod P is parabolic, then its image is closed and complete. The image is everything. That means G mod Q is complete, so Q is parabolic. For the second assertion, so the second assertion is slightly more involved. I won't show all the details, but let me give you the general idea. So you get to use this diagram here. So first of all, we have G mod P cross X. So X is any algebraic variety. We need to show that the morphism from G mod P cross X to X, given by projection in the second factor, we need to show that this is a closed morphism. It takes closed sets to closed sets. So, and in order to do this, we add all these embellishments here. So we first think about this projection map as factoring through first taking the quotient by Q and then projecting to X. So P is containing Q, so we can take a further quotient by Q and then project. So this triangle commutes. And we know that G mod Q is complete. So this projection map is closed. But that doesn't automatically give us anything here. We need to do more. So we write this commutative square here. So this map alpha from Q mod P cross G to X is kind of the action map for, yeah, it's sort of like an action map, not exactly, but sort of, which takes a coset QP here, an element in G, and takes G times Q, that coset of P. So it kind of extends the Q cosets for P to G cosets for P. And we also have the projection map onto G cross X. Since Q mod P is complete by hypothesis, since we assume that P is projective in Q, this projection map is a closed morphism. And here we just have the mod Q map. So we mod the G, we take the Q cosets. And so it's easy to see that this diagram commutes. All right, so in order to show, and remember what we need to show that this is a closed morphism. So let's start with something closed here. So let's call V, let's just fix a closed subset of G mod P cross X. So what we'll do is we'll pull it back by alpha. If pull back takes close to close, so that's something closed in here. Then we'll project it down here. So that's again closed because Q mod P is complete. So we get some closed subset here. And then, so this is the part that I won't go into too much detail. So this projection map in general doesn't take closed sets to closed sets, but for that specific closed set that comes from this procedure, it does. So then we'll get a closed subset here. That's the image of a closed subset here. And when we do this projection map, we'll get something closed. So that's the idea. Here I wrote it out in a bit more detail. So we take something that's closed. We first pull it back to something that's closed in this variety. That's just because alpha is continuous. Then we project it down and we get something closed because Q mod P is complete. And then Q will actually act on this image. So this is not just some arbitrary closed subset of G mod X. It's a Q invariant closed subset of G mod X. And that's why if we apply this quotient map, we'll get something closed. But that if we apply that quotient map, that's the same as since we just play around with the diagram and we see that's the same as just applying the quotient map from, I think there should be a tilde here, pi tilde Q. Apply that to V, so just kind of do the quotient directly. And then we finally use that G mod Q is complete. And yeah, that does it. So yeah, that's the proof modulo maybe this step of convincing yourself that this set is closed inside of G mod Q cross X. Right. So, okay, any questions on this proposition, its proof, or the previous proposition? All right, so let's go on then. Okay, so we say that a group is, so we have this definition. I think we might have seen this definition already. We say that a group is solvable if the following chain of subgroups stabilizes to the identity subgroup. So what is this chain? Well, first we start out with the group itself, then we take the commutator subgroup, and then we take the commutator subgroup of the commutator subgroup, and then we iterate this process. So at every stage, we take the commutator subgroup of the previous stage. And if at some point we get the identity group, then we say that the group is solvable. So it's immediate that any abelian group is solvable, because if we take the commutator, we just get the identity. This is a somewhat, you can think of solvability as a weaker version of something, of a group being abelian. So so it's somehow not too far away. And it's also related, I forgot the exact relation, but it's related to Galois theory and solvable. Yeah, maybe the reason it's called solvable is because if you have a field extension, in Galois theory, if you have a field extension and the Galois group is solvable, then something I forgot, but if somebody remembers, feel free to chime in. But then you get some solvability of something. Does anybody remember what it was?
That every polynomial is solvable by radicals.
By radicals, that's right. Okay, there we go. But anyway, that we're not too concerned about that. We just take this definition here. And we saw in an earlier lecture that if we take the subgroup of unipotent upper triangular matrices, then that's solvable as a group, because if we take successive commutators and we kind of we get more and more zeros in that upper triangular part until at the nth stage we'll just get the identity matrix. So you can similarly show that the subgroup of upper triangular matrices is solvable. That's just because if you do one step here, Bn commutated with Bn, if you take the commutator subgroup, you get Un, and then you already know once you get a solvable group in that series, then you know that eventually you'll get something. You'll get the identity. So the original thing must have been solvable. Right. Okay. So that's solvable. Okay. So here's the connection to parabolic subgroup. So let G be a connected linear algebraic group. Then G is solvable if and only if G contains no proper parabolic subgroups. So we already saw that if G is commutative, then it contains no proper parabolic subgroups. The only parabolic subgroup is G itself. But we see that in fact that's true for solvable groups. Before jumping into the proof, let me point out an immediate corollary, and that's that two of our favorite groups, GLN and SLN, are not solvable, because we've already demonstrated that there are parabolic subgroups in each of those subgroups. So, for example, upper triangular invertible matrices, and so that means that these two groups are not solvable. Of course, there are other ways to prove it, but once we have this theorem, it follows pretty quickly. Okay, so let's see how the proof of the theorem works. So first of all, let's prove that if G is solvable, then it contains no proper parabolic subgroups. And we do this by induction on the dimension of G. So if the dimension of G is 1, then we know that G is in fact abelian. So we argued that previously. So that means that G has no proper parabolic subgroups, as we already observed. Okay, so for the induction step, let's suppose that the dimension of G is bigger than 1 and assume that G is solvable. Okay, so let's take a parabolic subgroup of G, and we're aiming to show that there are no proper parabolic subgroups of G. So if we take just some parabolic subgroup of G, it must turn out to be all of G itself. Okay, so we have this P parabolic subgroup. So the first thing to do is to observe that if we take the commutator and if we intersect P with the commutator, then we get a parabolic subgroup of the commutator. Why is that? Well, because the quotient of the commutator by this intersection, that's isomorphic to if we took the subgroup generated by P in the commutator and modded out by P, and that'll be closed inside of G mod P, because this subgroup will be a closed subgroup. Okay, so we get a parabolic subgroup of the commutator. Okay, so what do we know about the commutator? Well, since G was solvable, its commutator must also be solvable, because it's the first thing that appears in the series. And also, since G is solvable, that series must, at every stage, we must decrease the dimension, because we know that eventually we'll get to dimension 1. So we must be, if we look at the corresponding sequence of integers, they must be strictly decreasing until you reach 1.
So you assume it's closed. So the commutator is closed?
Yeah, the commutator is closed, yeah.
Okay.
So because it's the image of a map of, yeah, you can show that it's closed. It's,
Okay.
yeah, by thinking about it as an image of a certain morphism. So then, yeah, so then by the induction hypothesis, we have this subgroup that's of lower dimension and that's solvable. So then it must not have any proper parabolic subgroups. So that means that this intersection must be all of the commutator subgroup. In other words, the commutator is contained in P. So, okay, and so now we're pretty much done. Why is that? Well, we know that the G mod the commutator is abelian, and we know that we have this subgroup P mod the commutator inside G mod the commutator, and that's since everything is abelian, that must be a normal subgroup. So the quotient of G mod the commutator by P mod the commutator, that must be affine, since we're taking the quotient by a normal subgroup. And this quotient is just isomorphic to G mod P. So, and it's complete since P was chosen to be parabolic, and it's also affine, so it must be just a point. So that allows us to conclude that G mod P is a point. So then G is equal to P. Yeah, any questions on this part? And just straightforward induction with the commutator. Right. All right. So then what about the other direction? So now we want to show that if G has no proper parabolic subgroups, then it must be solvable. So first we show this claim that if we have no proper parabolic subgroups, then anytime we have a representation of this group with no proper parabolic subgroups, there's a basis of V on which G acts by upper triangular matrices. So this is actually a theorem that appears later on. Yeah, the Lee Quotient Theorem. So, so why is this claim true? Well, again, you prove it by induction. So induction on the dimension of V. So if V is one-dimensional, there's nothing to show because then then every matrix is upper triangular. So let's assume that the dimension of V is bigger than 1. So we mentioned earlier in the class that anytime we have a group acting on a variety, there is a closed orbit. Not every orbit is closed, but there is a closed orbit. We can always assume that we can always take a closed orbit. So let's take a closed orbit inside of the projective space of V. So G acts on V. G is assumed not to have any proper parabolics. Now G acts on the projective space of V, and we take a closed orbit. So since X is closed inside of the projective space, X itself is a projective variety. And since it's an orbit, it has a transitive G action. So that means the stabilizer of any point is a parabolic subgroup. So things, quotients of G that are projective varieties are parabolic subgroups. Yeah, quotients of G by a subgroup being a projective variety means that that subgroup is parabolic. However, we assume that there are no proper parabolics in G. So if we have a parabolic, it must be all of G. Yeah, so, and what was that parabolic? It was the stabilizer of a point. So if the stabilizer of a point is all of G, that means that that's a fixed point and its orbit is just itself. So this X, this capital X consists of just a little point, the point little x. So that's, we've used the induction hypothesis already. So what is this? How do we use this point? So this is a point in the projective space of a vector space. So that means it corresponds to a line. So it's the span of some vector, non-zero vector in the vector space. And since this line is fixed in PV for the G action, that means that when G acts on the vector V, it must take it to a multiple of itself. It must be on the line, because we know that if we pass the projective space, then that point doesn't move. So in order for it not to move in projective space, it must just be sent to another point on the line. So G dot V is always in the span of this vector, in the K span of this vector for any group element. So that means, okay, so what do we do now? Well, we can take W to be the quotient of V mod this span, mod this line. And we know, this implies that this line is preserved by the action of G. It's stable. So if we take the quotient, we get another representation of G. So this representation has lower dimension. And so now we can apply the induction hypothesis. Remember, we were doing induction on the dimension of V. And that means we can pick a basis for W. So W has dimension, I guess, N, I'm calling the dimension of V. So W has dimension N-1. So we just pick a basis, and we can pick the basis in such a way that G acts by upper triangular matrices. That's where we use the induction hypothesis. And now the rest is pretty simple. So now we just pick lifts. So W is a quotient of V by some subspace. We have this basis of W. So to get a basis of V, we just pick any lifts of the W's. And we also need to add in this V here, which is the thing, which is the span of V is the thing we quotiented it by. So if we just add V to the set of lifts of the W's, then we get a basis for V, for capital V. And now it's pretty clear. If you're not convinced, you can just write it out a bit more, but G will act by upper triangular matrices in this basis. So we already know that the first, so if we think about G, every element in G as a matrix in this basis, then the first column will just have some scalar in the top entry and zeros elsewhere, because we know that V is sent to a multiple of itself. And then for the remaining vectors, for the remaining columns, we use the fact that we chose this basis for W, in which G acts by upper triangular matrices. Okay, so that proves the claim. So now we've shown that so a group is solvable if and only if it contains no proper parabolic subgroups. Oh wait, okay, so that's just the claim. So how do we use the claim to finish the theorem? Well, that's easy, because we just embed G inside of GLV for some V, and then we use the claim, and we show that G embeds into the subgroup of upper triangular matrices, Bn, and we know that this is solvable, so G is also solvable. Any subgroup of a solvable group is again solvable. Right, so now we've completed the theorem. Okay, any questions on this theorem I just explained? Okay, so next result is what's known as Barreau's fixed point theorem. It says the following: so if we have a connected solvable linear algebraic group acting on a complete variety, so X is a complete G variety, then there exists a fixed point. So there exists a point on X that's fixed by all elements of G. Why is this? Well, we know that there's a closed orbit. So we take that closed orbit, we take a point in the closed orbit, we take the stabilizer. So so the orbit is G mod that stabilizer, and it's a closed subvariety of a complete variety, so it's again complete. And that means that H has to be parabolic. And since G is connected and solvable, since G is solvable, we just showed that there are no proper parabolics, so that means that H is equal to G. And so that orbit consists of just the point X, and it must be fixed by all elements of G. So that's Barreau's fixed point theorem.
Why G mod H is complete again?
So any closed subvariety of a complete variety is again complete.
Why the quotient is complete?
The quotient is complete because it's a closed. So the quotient is the orbit. The orbit is closed, and it lives inside of a complete variety. So it must be itself complete.
Oh, so you identified it as the orbit. Okay, thank you.
Yeah. So yeah, anytime we have an orbit and we pick a point, then we can identify the orbit with G mod H. Okay, everybody good with this theorem? Okay, so now we're ready for definition. You may be wondering why I was using this notation B for this subgroup of upper triangular matrices. So the reason is it's a Barreau subgroup. So what's a Barreau subgroup in general? So a Barreau subgroup of a linear algebraic group it's a closed, connected, solvable subgroup that's maximal for these properties. So it's the maximal closed, connected, solvable subgroup of G. It's a maximal closed, connected, solvable subgroup of G. It doesn't need to be unique. Right, so that's the definition. So before giving some examples, let me state some facts. First of all, any conjugate of a Barreau subgroup is again a Barreau subgroup. Second, any Barreau subgroup is in fact parabolic. And third, if we have, so we can give another characterization of parabolic subgroups in the following way: a closed subgroup of G is parabolic if and only if it contains a Barreau subgroup. So this is an equivalent definition of a parabolic subgroup. It just needs to contain a Barreau subgroup. So yeah, so this is so Tal, you were asking what an analog of parabolic is for compact Lie groups. This is it. So Barreau subgroups still make sense. So solvable, because solvable is a notion for abstract group. It doesn't need to be a linear algebraic group, and we can ask for a maximal closed connected solvable subgroup of a compact Lie group, and then any group that contains a Barreau subgroup will be parabolic. Okay, so that's part 3. Part 4 is that any two Barreau subgroups are conjugate. So yeah, so Borel subgroups are not unique, but they're unique up to conjugation. So let's see how the proof of this goes. So yeah, we can just assume G is connected throughout. So the first statement is pretty immediate from the definition, because if we conjugate, if we Borel subgroup, it's still some other subgroup that's maximal with respect to those properties. For 2, we do it by induction on the dimension of G. So first of all, if the dimension of G is 1, then G is abelian, so it's solvable. So its only Borel subgroup is G itself, which is parabolic. So if G is and if so, that takes care of dimension equals to 1. If dimension is bigger than 1, then well, there's 2 cases. First, if G is solvable, then again the maximal solvable connected subgroup will be G itself. So it has only one Borel subgroup, and that's itself. So it's parabolic. The second case is what happens if G is not solvable. Then we know that there's a proper parabolic subgroup of G. So we showed that solvable is equivalent to having no proper parabolic subgroups. But if it's not solvable, then there must be some proper parabolic subgroup of G. So let's take a proper parabolic subgroup of G. Let's take a Borel subgroup of G. So some Borel subgroup of G. And what we aim to show, what we'll actually show is that P contains a conjugate of B. So maybe P doesn't contain B itself, but it will contain a conjugate of B, which by part 1 is another Borel subgroup. Okay, so how do we do this? Well, let's think about the action of B on G mod P. So G mod P, since P is parabolic, that's a complete variety. And there's this left action of G on G mod P. We don't think about all of G acting, we just think about B acting. So the action just takes the coset of little g to the coset of B times G. So this is an action of a connected solvable group on a complete variety. So by Borel's fixed point theorem, which we just saw, there must be a fixed point for this action. So there must be a point, there must be a coset. So any point is just a coset. So there must be a coset inside G mod P such that B acting on this B fixes this coset for every little b in B. And if you just rearrange things here, you see that this conjugate of B lies inside of P. So Borel's fixed point theorem allows us to conclude that a conjugate of B is inside of P. So yeah, okay. So but we're not quite done. We still need to show that we still need to show that B is in fact parabolic inside G. And here we combine the induction hypothesis with the sort of transitivity property that I stated earlier. So first of all, okay, so without loss of generality, we can assume that the Borel subgroup we chose was in fact this conjugate, so it lies inside of P. Okay, so because Borel subgroups are defined by this maximality property, we see that that B must be in fact a Borel subgroup of P. If we had if there was some bigger connected solvable closed solvable subgroup of P, then it must also be such a subgroup for G, but then B would not be a Borel subgroup. So B is a Borel subgroup of P. And now P is proper, right? P, since we're in the case where G is not solvable, we chose P to be a proper parabolic subgroup. So that means the dimension is less than G. So that means, so we apply the induction hypothesis and we see that B is parabolic in P. And since P is parabolic in G and B is parabolic in P, we see from this earlier result about this transitivity property that B is itself parabolic in G. So there we go. So we've proved that any Borel subgroup is parabolic. It's a parabolic subgroup. Okay, that was only part 2. For part 3, part 3 says that a subgroup is parabolic if and only if it contains a Borel. So in fact, if it's parabolic, then it contains a Borel. That's part of the proof we just did. So we looked at we took any Borel and we looked at that action on G mod P, and there's a fixed point for that action. So that tells us that a conjugate of that Borel lives inside the parabolic we started with. And what about the other way? Well, so here we need to show that if subgroup contains a Borel subgroup, then it's parabolic. But any subgroup containing a parabolic subgroup is itself parabolic, and we just showed that B is parabolic, so that subgroup is parabolic. Okay, so hopefully that makes some sense, but it's pretty straightforward. And finally, okay, maybe I won't go through the proof of this last part in detail, but we again use, if we have two Borel subgroups, we look at the action of one of them on the quotient by the other, and so B acting on G mod B prime. Then we also look at B prime acting on G mod B. We use the Borel fixed point theorem. That tells us that a conjugate of one lies inside the other, and the same thing the other way around. And since they have the same dimension, they're in fact conjugates of each other. Okay, so let me point out a few more results. I know yeah, let me just point out these last few results. I might go 1 or 2 minutes over time, sorry about that. So first of all, if we have a surjective map of linear algebraic groups, then it takes parabolics to parabolics and Borels to Borels. And yeah, so I won't say anything more about the proof, but it's pretty straightforward based on what we have already. So yeah, I think I just want to end today with telling you about this exercise. So there will be this exercise assigned today, which will show that, in which I'll ask you to show that this subgroup of upper triangular matrices is in fact a Borel subgroup. So yeah, I think maybe you see it already, but you have all the tools at your disposal. That's part A. Part B is that any Borel subgroup of G is of the following form. It's a stabilizer of some complete flag. So flag, like we pointed out, is this increasing sequence of subspaces of Kn. So we have a one-dimensional subspace, two-dimensional, and so on. And they're contained in each other. And if we take any flag and we look at its stabilizer, so there's GLN acts on flag, so we think about its stabilizer, that'll be a Borel subgroup, and any Borel subgroup has to be of this form. Okay, so yeah, I think I'll stop here for today. I can still stick around for another minute or two if somebody has questions.